going to do one more exercise with absolute extrema. Now, remember in the first video I mentioned that if the function is continuous on the closed interval, then it has an absolute mean or an absolute max, at least one of each, right? So it has its absolute extrema are achieved in the interval. Now, you have a rational function here. You have to be careful to see that the function, to apply this theorem, has to be continuous on the whole interval. Now, how can a rational function be not continuous? Well, it is not continuous when the denominator is 0. Now, if you look at the denominator of this function, x squared plus 1, x squared plus 1 is never equal to 0. On the reals, right? If x is a real number, this cannot ever be 0. So that tells you the function is continuous, the theorem applies, therefore we do the same procedure. We take our first derivative, and now the kicker or the difference here is that we have a quotient, so we do quotient rule. Derivative of the top is 4 times the bottom minus the top times the derivative of the bottom, which is 2x all over the bottom squared. And when you simplify this is going to give you a 4x squared, and this is going to become minus 8x squared. So this all becomes negative 4x squared plus 4, as I say 1, remember you have to distribute here, plus 4, that over x squared plus 1 squared. You could factor, if you want, you could factor a negative 4 out of that, and you get x squared minus 1 over x squared plus 1 squared. And that's as simplified as you can get it. So now we need to find, that was step 1, we need to set it equal to 0 to find those points where the derivative becomes 0. Now, the derivative of this function is always defined because the denominator cannot be 0, as we mentioned before. So the only way that you have a critical point is when the function, or the derivative of the function is 0, and the derivative of the function is 0 when its numerator is 0. So the top is 0. So you factor this, and you could divide by negative 4. So you're left with just x plus 1 times x minus 1. When you divide by negative 4 on both sides, that negative 4 goes away. And you are left with two critical numbers. The first one is negative 1, and the second one is positive 1. I get those when I set each term individually equal to 0. That is because the product of two real numbers is 0 only when one of them is 0. So you set each one of them to 0 and find out your two critical numbers. So now all you have to do is evaluate your function, the original function, because we're looking for absolute extrema, at the critical numbers and the endpoints. I guess I didn't put them in order. It really doesn't matter. But you evaluate it directly into the function. Let's do f of negative 1. That would be negative 4 on top. Then the bottom would be negative 1 squared is positive 1, plus 1 is going to be 2, and the whole thing is going to be negative 2. When you do negative 3, the top would become negative 12. The bottom would be negative 3 squared is 9, plus 1, 10. So it's going to be negative 6/5. And for the other ones, notice that this function, when you evaluate the denominator, is the same thing, whether you evaluate it at negative or positive 3, and then the top changes sign, so this whole thing is just going to be 6/5. And by the same reasoning, the f of 1 is 2. Alright, so let's see. We have then the smallest number is going to be this one, and the largest is going to be this one. So you'll have an absolute min at x equals -1, or if you want, you can write it as a point, and you're going to have an absolute max at x equals 1, or if you want, you write as 1, 2. And you can look at the graph, and my graph is a little far. Let's pull it up a little bit. There you go. So if you see here -1, you have a relative min, an absolute min, sorry, for the interval between -3 and +3. And then at +1, roughly, you have your max 1, 2, -1, -2, or other points you see where neither, at the endpoints we had neither an absolute min or an absolute max. So that's that for this problem. As you see, the only difference this time is the function was a rational function, so we had to be a little bit careful with the denominator possibly being 0. And in that case, if there would be an asymptote in the interval, then we would say that the theorem doesn't apply, and we probably would not have a min or a max. We'd have to analyze that. But in this case, the function is continuous. So we know by the theorem that it'll have an absolute max and an absolute min. And we follow the same procedure. Given that we have a quotient, we have to do a quotient rule, but that's not anything more difficult than what we have already done. The procedure is pretty much the same. So that's that. That's basically all I have for this section. I'll continue with section 2.5 in the next video. Thank you for watching, guys.